Welcome everyone to this Timeloop and Accelergy tutorial to be held in conjunction with ISCA. My name is Angshuman Parashar. I work at NVIDIA, and this tutorial is as a result of a joint collaboration between MIT and NVIDIA. And the two tools being presented here, Timeloop and Accelergy, are also as a result of a collaboration between MIT and NVIDIA. You can see the list of the other people involved in putting this tutorial together. We have Tsai, Nellie Wu, and Joel Emer with us in this recording. Nellie will be presenting the second half of the tutorial on Accelergy later. I will be presenting the first half of the tutorial on Timeloop. Specifically, the part of the tutorial we're covering today is the lecture component. We will later have a hands-on practical set of exercises that comes later this week. Okay. Before we begin, here is a set of resources. Feel free to pause this video and go through the links. The most important link over here is the tutorial website, which is the first link. And the rest of the other links should be available on the tutorial website itself, which includes the Docker that you'll need to download and all of the other infrastructures, references to papers, etc. Okay, let's begin the main technical content. So first, let's begin with some motivating remarks. Why are we doing what it is that we're doing? Why is everyone potentially interested in these tools? So what we're looking at is the space of architectures of DNN accelerators. And when an architect is designing a DNN accelerator, there are, if you sort of zoom out, take a number of steps back, and look at the big picture, you're worried about two main things. You're worried about data movement, and you're worried about arithmetic, right? So the data movement is to bring the data in from your memory or storage devices and to your arithmetic units. And for the most part in this tutorial, we'll be focusing on data movement, although the tools are actually capable of measuring arithmetic activity as well. Most of the interesting trade-offs that we've seen actually arise from the data movement aspect. So why is data movement important? Well, it's because there's a huge difference in the amount of energy that it takes to perform a computation, such as an 8-bit integer multiply in this example, and the energy required to fetch the operands for that computation from some storage element, such as DRAM or even a large SRAM. You can see that even for a large SRAM, there's an order of magnitude difference in the amount of energy it takes to fetch the operands. And so if you're fetching every operand from a large storage device, then you're going to be consuming an insane amount of energy just fetching operands and putting results back in. Fortunately, here's just an example DNN layer. What you see is that the number of operands is the relationship of the number of operands with the number of arithmetic operations is roughly a 3 order of magnitude difference. And so what that means is that basically there's a ton of reuse of the same operands to perform a large number of computations. And so that actually gives us a bunch of hope. So we want to be able to try to take advantage of that reuse. The other interesting fact is that reuse actually exists along various dimensions. And so here's an example of a seven-dimensional network layer with a bunch of filter weights, an array of input activations, and an array of output activations. Across this entire layer, you're going to see several forms of reuse. You're going to see convolutional reuse as you slide this filter across the plane of inputs. And so you end up reusing the filter. You see a bunch of input activation reuse because multiple filter blocks will actually be applied to the same set of inputs. Okay, you'll see output activation reuse, which is an interesting form of reuse, but it's sort of a reduction reuse, because what you're going to be doing is across these input channels, you're going to be performing an accumulation sum. And so that ends up reusing a bunch of output activation locations. And finally, there's batch reuse. In a lot of applications, you're actually performing this operation on a batch of input activations, in which case you're going to be reusing the entire filter weights across every instance of that batch. So there's all of these forms of reuse, but then we have to map this reuse, we call these forms of reuse as algorithmic reuse. And we need to map all of these forms of algorithmic reuse onto a hardware array. And a hardware array is typically, I've just shown a cartoon here, is typically a 2D array of some sort of form of a processing element. And so what ends up happening is that to exploit this reuse, you need to map basically this algorithmic reuse into hardware reuse. And what do I mean by hardware reuse? Well, think about when we design hardware, in what ways can hardware take advantage of reuse? Well, there's your classic temporal reuse, wherein you fetch something into a smaller storage location, such as a small register file or a cache, and you reuse that value from that register file instead of having to refetch it from the more expensive DRAM. And that's actually, it gives you significant energy savings if you do that. There's also other forms of reuse. So here's an example. This cartoon is showing an example of a hardware-based multicast. And what that's doing is you're fetching something from an expensive buffer, but then you're multicasting it using some sort of a hardware network to multiple receivers. And so what that means is even though multiple receivers are receiving that element, you just did one read from the parent. So that's another form of reuse. And a third form of hardware reuse is what we call forwarding, in which a hardware unit uses a value and then forwards it on, for example, to a peer unit. And all of these forms of reuse are what we call hardware reuse. And so during the course of mapping, you're going to be mapping algorithmic reuse to hardware reuse. And so a natural question is, what are the different ways in which we can do that? Is there exactly one way in which we can transform this reuse, or are there multiple ways? Well, it so happens that for a lot of accelerator architectures, especially flexible architectures, there's actually millions of ways to do that. And we call these mappings. So there's millions of alternative mappings of a single workload onto a single architecture, okay? And so a natural follow-up question to that would be, okay, are these mappings interesting, or are they all kind of silly permutations of the same way of doing things? Do they actually matter? And what this slide is trying to show you is that yes, it does matter. This slide is showing you a motivational experiment. It's a specific experiment conducted on one workload and one architecture. So the workload and architecture is not changing, but the mapping is changing. And the x-axis shows you picojoules per Mac. Basically, it's an energy. It's an energy measure on the x-axis, and the y-axis is showing you the number of mappings that falls into a particular bucket of energy efficiency. And so this is basically a histogram. Okay. And so overall, this picture is capturing 480,000 mappings. The delta between the most efficient mapping, which is on the left-hand side of this chart, to the least efficient mapping, which is on the right-hand side of this chart, is 19x. Okay, and of these, only one actually happens to be optimal. It's one of these in the optimal bucket. And there are 9 other mappings which are within 1% of that optimal mapping. So what you see is that a very, very small number of mappings are actually optimal. And so what does that mean? That means that if you're thinking about modeling, right? If you're thinking about doing a performance and energy characterization of a workload on an architecture, you really need to consider the mapping, because without the mapping, you're not going to be getting any meaningful results. And so what that means is, if you're trying to build a model, you have to build a mapper, because without a mapper, you're not going to be finding an efficient mapping. And look at the large number of mappings possible. It's unlikely that a human is going to be able to arrive at the optimal mapping for a large number of workloads across a large swath of architectural choices if you're doing an architectural design space suite. Okay, so a model needs a mapper in order to do a faithful evaluation. But there's another interesting thing that's happening here. Of these 480,000 mappings, 6,500 of those mappings have the same exact DRAM number of DRAM accesses, okay? And they're all the minimal number of DRAM accesses. And so, although they have the same number of DRAM accesses, those mappings vary 11x in energy efficiency. So what does that mean? That means that you cannot use the number of DRAM accesses as a measure for what a good mapping is, because a bunch of good and bad mappings have the same number of DRAM accesses. And so what that's saying is that even a mapper, while it's searching across a space of mappings and trying to find the best mapping, it needs a good cost model to tell it what a good mapping is versus what a bad mapping is, right? And DRAM accesses is not a good cost model. It's an insufficient cost model, at least in this example. And so what we see here is that a model and a mapper have this interesting synergistic relationship. They need each other. And that feeds into this infrastructure that we've built, which is the combination of Timeloop and Accelergy. I won't go into the details of each of these boxes on this slide. We'll do it later in this presentation. But basically, the broad idea is we're talking about two halves of the game here. The model half, which contains Accelergy, whose intent is to model a variety of DNN accelerators, and the mapper half, whose intent is to find an optimal mapping. And the mapper has to be able to target every single architecture that the model is able to model. Okay, so why use these tools? I think that we've done a bunch of work on these tools, and there's a bunch of attributes that we think make these tools worthy of investigation. The first is that the microarchitectural model, which is part of Timeloop and part of Accelergy, is very expressive. It's a generic template-based model that covers a range of hardware architectures. It's fast. In fact, it's actually faster than native execution on host CPUs, right? Which is not something that you see in typical simulators. It's about an order of magnitude faster, give or take, depends on the complexity of the architecture. It's also accurate. We'll cover some validation experiments soon. The technology component of this, so the technology model, which is specifically encapsulated in Accelergy, it allows for a complex user-defined architectural components, and Nellie will be going through a bunch of that later. And it supports plugins for a variety of technology models. It's got a plugin for Cacti, plugin for Aladdin, and also you can have plugins for proprietary databases if you're working in a corporate environment where you have access to a proprietary database. You can wrap that together in an Accelergy plugin and import it. And then, of course, I spoke about the mapper. Timeloop has this built-in mapper, which addresses the hard problem of optimizing data reuse. Okay, so let's walk through some of the experiments that we conducted to validate Timeloop. So the first experiment is one in which we validated versus IRIS, specifically the IRIS energy model that was used in the ISCA 2016 publication. On the left-hand side is reference data from that publication. On the right-hand side is a set of experiments we reproduced using Timeloop. The x-axis shows a set of workloads, and the y-axis shows normalized energy. And each of these colors shows a particular component of the architecture. And so this is an energy stack. And what you'll see is that roughly we're within 5 to 10% error for almost each of the workloads here. We also conducted another energy validation experiment versus a PE from the Simba architecture. This was an NVIDIA work that was published last year. So on the x-axis, again, is a set of workloads. Specifically, they were taken from the Bench suite. And the y-axis, again, is the normalized energy consumption, and with an energy breakdown for various components. And overall, what we see is we're within 8% error across all workloads. In terms of performance, what we see is this is again versus Simba. For the most part, we are within a 10% error. There are a few outliers, and that has to do with the fact that at least a few of the outliers were because the hardware was laying out data in intermediate buffers that was a mismatch for the pattern in which the data was being filled. And so what that meant is that the data was being filled and read out. And so that mismatch meant that it wasn't pipelining. The hardware buffer wasn't pipelining the fill of the data with the read of the data. And Timeloop, when it's modeling hardware, it assumes that you're always able to pipeline. And in this case, the architect told us that with a simple change to the hardware state machine and their configuration generator, they will be able to match what Timeloop expects it to do. Okay, so let's walk through some case studies. So these are some experiments we conducted using the infrastructure. They just highlight a few different ways in which you can use the tool. So the first case study is actually very, very interesting. So this is focusing on the need for a good technology model. So let's look at the left-hand side chart first, the A part of the chart. The x-axis, the big the big steps on the x-axis refer to a particular workload, so Con1, Con2, Con3, etc. And then within each workload, we're looking at two bars, each corresponding to a different technology node, so 65 nanometer and 16 nanometer. And then the y-axis shows an energy breakdown, and it's stretched out to be normalized, right? So it's just a percentage energy breakdown. And what this is showing is that the energy breakdown, so by the way, this is for the same architecture and the same set of workloads, right? And so what you see is that even for the same architecture and the same workload, as you move across technologies, the energy, the contribution of various components to the energy stack changes. And so what that means is it's really important to have a technology model. Otherwise, you're not going to get a good characterization of the architecture, and that should be fairly obvious. Now, as we move forward in technology from 16 nanometer to 7 to 5, etc., you can expect this distribution to continue to change. In which direction, we don't know. But that's why it's important to have a technology model in place for architects. Now let's move on to the right-hand side. So this is an even more interesting experiment. Here, it's the same architecture. It's the same workload. It's actually the same technology, but it's a different mapping, okay? And so what's happening here is the difference between the left bar and the right bar is that on the left bar, even though this is a 16 nanometer architecture and the experiment is conducted on 16 nanometer, we use the mapping that the mapper found as optimal for 65 nanometer. And we use that same mapping on the 16 nanometer architecture. Versus the right-hand bar, what that is doing is rerunning the mapper, now with the 16 nanometer model in loop with the mapper. And now you can see that the mapper comes up with a different mapping, which is even more optimal for 16 nanometer. So what is this showing? This is showing that it's really, really important to have an accurate cost model in loop with the mapper. Otherwise, the mapper may produce a mapping which is not portable across technology generation, right? So that's one case study. The next case study is something that a typical architect would do, okay? So this is a set of workloads, the same technology, and what this is doing is it's changing various architectural configurations. So in fact, the left-hand bar is sort of the nominal iris-like architecture that we use for this experiment. That was described in the paper, the ISCA 2016 paper. And what we observed was that there were a number of accesses that were going to the register file. In fact, we didn't observe it. The iris architects actually observed it. And so one experiment that we conducted together with them is, hey, what if we added a single register to sort of filter out some of these accesses? And that's what you see as the second bar. And you can see across all of the workloads, there's a dramatic reduction in energy efficiency as you move from the shared register file into this this filtered architecture with a single L0 register. And then the third bar actually represents what the final iris architecture, the final iris chip, the architecture that the chip used, which is actually a very optimized partitioned register file, in which the RF was separated out into 3 partitions, one for each data space or tensor that it was accessing, and the size of each of those partitions was carefully curated and architected to make sure that it fit the requirements of the data flow that it was using. And you can see that with that sort of an optimization, you see an even bigger energy efficiency improvement. Okay, so with those introductory and motivating remarks out of the way, let's dive a little bit into how do you use the infrastructure, how do you use Timeloop. In these slides going forward, we will be using Accelergy in a transparent way. So we won't be talking too much about Accelergy. In the hands-on tutorial and during the Accelergy section of this lecture, Nellie will be talking about a lot more about actually how to invoke Accelergy itself. Okay, so let's focus on how you use the Timeloop model. So we will be ignoring the mapper for now and just talking about invoking the model. And so we're focusing on the model. So what do you need in order to invoke the model? You need to give it a problem, which is what is the algorithm you're trying to map? And this is an example of a CNN layer. You need to give it an architecture, of course. That's the architecture you're trying to model. And because you're not using the mapper, you need to give it a mapping, right? We need to tell it exactly how to take that problem, chop it up, and distribute it and schedule it on the hardware. And I'll explain how you do that. Okay, so given these three inputs, the model will be able to do its job. But let's talk about each of these inputs using some examples. So as we go through these slides, I'll be showing these examples, but I won't go too much into the detail of actually coding up and representing them and running them in Timeloop. We'll be doing that during the hands-on exercises. They'll be using roughly the same set of problems. But for now, let's think about how you represent them, right? So this is a very, very simple example of a problem. There's a 1D convolution, and the loop nest here shows how we would naturally represent this convolution. I've got a loop over R, which is the filter weights. I've got a loop over P, which is actually the size of the output activations. And then this is the equation that I do, and you can see this indexing expression of P plus R, which actually ends up achieving the sliding window that you need to perform a convolution. And this little picture here shows you a representation of the various tensors, R filters, P outputs, and P plus R minus 1 input activations. Now, to represent this in Timeloop, you need to think about a few things. One is what we call the operation space, which is shown by this yellow box here. And that is, what is the space of arithmetic operations, or what is the space of instances of the loop body as part of this loop nest? So every instance of this statement, the multiply add operation, is actually, think of it as a point inside this rectangle. So how many points in this rectangle will we have for const? It's going to be P times R, right? That's why it's a 2D square. And then you need to think about data spaces, and the data spaces are basically the tensors that you're operating on as part of this problem, right? So we've got weights, inputs, and output activations, and from the color coding, you should be able to correlate that back to this picture. And finally, you need to think about the projections, which is how does this operation space project into the weights? And this projection is nothing but basically your indexing expressions. Right? So your indexing expressions for these tensors are defining how every map operation projects onto a particular coordinate in your weight tensor, a coordinate in your output tensor, and a coordinate in your input tensor. And these are the three things that we need to provide Timeloop, and we do that via a YAML representation today. So what we're writing here is we're declaring a problem, and within the problem key, we have two main subkeys. We have the problem shape and we have the problem instance. So the shape describes the overall shape of this loop nest, and the instance just instantiates one of those and that forms a particular workload that you'll be evaluating. So let's dive deeper into the shape. You've got a string name, and then you declare the dimensions, which is R and P. And so these are the dimensions of the operation space or the iteration space. And then you define a set of data spaces. I've got weights, inputs, and outputs. These are free from form strings. You can use whatever you want to. And then you describe a projection. So for the weights, my projection is R. And so this is basically a sum of products notation to describe these indexing expressions. And we'll get more into this during the hands-on exercises. But for now, just think of this as a way to represent these algebraic expressions. So for weights, it's really simple. We take the R that was defined above, and that R is the only index that I need to use to index my weights. For input, it's still one index, but it's the sum of P and R. And as I said, this is sum of products notation, and that's why you write P and R in the list. And for outputs, again, it's very simple. It's just a single dimension P. And outputs, we need to make a special note here that this is a read-write data space. And so Timeloop knows that you're going to be performing read, modify, write operations to this data space. Okay, so that's my problem spec definition. Now let's define an architecture. And this is a really, really simple architecture. I've got a single PE with a buffer and a single multiply add unit next to that buffer. The way you represent that is, again, a YAML. And we use this hierarchical tree-like architecture representation. Nellie will be talking a lot more about these either during the lecture or during the hands-on tutorial, because Accelergy and Timeloop share the same architecture spec formulation. So the way you write this out is that because it's a tree, you've got an architecture as the root of the tree, and then you define the subtree within that. And within that subtree, basically today we just have one node. The name of that node is a PE. And then we've got some local elements to that node. Specifically, we have two local elements, a buffer and a mat. For each element, we need to define a class and a set of attributes. So buffer here, the class is SRAM, and the attributes are specific things that class understands. So in this case, for an SRAM, we can define a set of entries. We can define the number of instances. This will become more interesting later on. And we define the number of bits in each entry. There's a bunch of other attributes that you can use to get more and more fidelity. These attributes are supported by Timeloop and Accelergy, and we'll cover more of these during the hands-on exercises. And then we've got the MAC itself, which is basically an integer MAC unit, and the attributes here defines the width of the unit. Okay, so we got the architecture and we got the problem. Now we need to describe the mapping. And in this case, because it's just a single buffer and a single map, there's not much choice you have in the mapping. So I used a particular loop nest here with R in the inner loop and P in the outer loop. You could have swapped them. That would be a different mapping. But in this case, because you're fetching everything from the same buffer, the two mappings will actually not have any difference in terms of their energy efficiency or performance characteristics. They would be identical. However, you technically still have a choice. But to represent this specific mapping, we still write a YAML. Everything in Timeloop happens with YAMLs. And what you describe is at a target. So even though the mapping is actually describing the data movement behavior between the buffer and the MAC unit, we conventionally attach everything that happens between stages to the outer level. And that's why the target for this section of the mapping is the buffer. And what we say is that at the buffer, we're describing a temporal mapping attribute, and we'll cover more about these classes of attributes. And what we're basically trying to encapsulate is this loop nest, right? So what are all of the things we need to describe this loop nest? We need to describe the factors, which are the loop bounds. So R equals 3 and P equals 16, which just says these are the bounds that you need to run the loops to, and the permutation. And the permutation always goes from inner to outer. So my innermost loop is over R, and my outermost loop is P, and that's why I write R and P. And if you give Timeloop this information, it basically interprets it into this loop nest. So now we've provided Timeloop with a problem, an architecture, and a mapping. We can actually invoke the tool now. And remember, this is Timeloop model we're invoking and not the mapper. And so it's important to fire Timeloop-model. We give it arch.yaml, problem.yaml, and map.yaml. And these are the outputs that Timeloop spits out. First is it actually spits out the mapping that you provided it, and you can see that it's spitting it out in loop nest form. And so now you can confirm whether the YAML you wrote was actually correct or not. In this case, it was. We're getting basically the exact loop nest that we intended. But additionally, it gives you some useful information. It actually tells you the tile sizes of each of the tensors or each of the data spaces at that buffer. So that's often useful for debugging, for figuring out what the heck is going on, and just to tell you if you're making use of your buffer space optimally or not. And it also spits out stats. It's a model, so it's going to spit out a bunch of stats. You can see a bunch of ellipses here, which means there's a lot of detailed stats for every single level of your architecture's hierarchy. It's going to spit out detailed stats for that. And then it's going to spit out some summary stats about the overall utilization of the architecture, cycles, energy, and so forth. You can see that some of the stats are 0 here because we just used the toy model to run this, a toy technology model to run these experiments for, you're going to be seeing meaningful statistics if you use a meaningful plugin. Okay, now let's step it up a notch and get to a more complex example of an architecture. In this case, we're just adding one more level of the hierarchy. We're adding a main memory to this PE. And to represent that, remember I said the architecture is a tree. What you see is you just sort of introduce one more node of this tree, which is this system block. Within that, your local element is this main memory, which corresponds to this block here. Its class is DRAM, and it's got a set of attributes. And underneath that local, sorry, not underneath that local, it's underneath this subtree. But alongside this local, you have its subtree, which is basically the PE subtree, and that's identical to what we described before. Okay, so that's the architecture. Now, in order to describe a mapping for that architecture, now the mapping has gotten more complex because we've got one more level in the hierarchy. We now need to describe a level of the loop nest for each level of the hierarchy, right? So we were already doing something for the buffer. Now we specifically for the data movement between the buffer and the MAC. Now we need to describe the data movement between the DRAM and the buffer as well. And so what you see is you see some loops that are in dark black and other loops that are grayed out. And the grayed out loops are sort of these nominal loops that run from 0 to 1. They're actually ignored by Timeloop, but this is sort of what we call a canonical mapping representation, and we just write it out for completeness, and it helps make sure that we're not making any errors, and it sort of helps draw the complete picture of what's going on. So all I've done is basically I've partitioned the old loop PNR. It's the same problem as before. It's the same workload. I just went over the P's in the buffer and then over the R's at the DRAM. Okay. And this is something that we call a weight stationary mapping. And the reason for that is at the buffer, you're going across P's. So what that means is if you're going across P's, you're going across the output activations, but you're not going across the weights. So that means as you're going across this innermost loop, you're holding the same weight stationary. That's why it's called weight stationary. And if you carefully think about, oh, what's the buffer occupancy for this weight stationary loop? What are the main memory access and what are the accesses to the buffers? You'll be able to reason out these expressions, and you can pause the slide and figure these out, reason about these for yourself. Hopefully you should come to the same conclusions. And in the hands-on tutorial, we'll be running this on Timeloop, and you'll be able to confirm whether the intuition was true or not. Okay, so how do we represent this? It's very simple. You know, we already showed you how to target the buffer. You now need to create another segment of the mapping spec that targets the main memory. And remember what I said, nominally, a target of main memory means you're talking about the data movement between main memory and the level underneath it, which happens to be the buffer. And so what this is saying is R equals 1 and P equals 16 over here, R equals 3, P equals 1 over here. And now you have to be careful about the permutation. It's inner to outer, inner to outer. Actually, within this level, you don't care about the permutation because R is 1, so it doesn't really matter. Now, remember what I said about this being the nominal representation where we write out the sort of grayed out 0 to 1 loop nest. Oh, by the way, one more thing I failed to mention in case it wasn't obvious. These are this is an inclusive brace and an exclusive parenthesis. So when I say 0 to 1, that means I'm just talking about index 0. Okay, so these loops, even though they're sort of optional in this high-level loop nest representation, they're not optional in this mapping representation. So when you provide a YAML mapping to time loop, you need to explicitly write out R equals 1, otherwise it won't know. When we talk about the mapper later, the mapper can figure all of this out, but we're using the model bear, so you have to give it everything. Okay, so now for that same architecture and the same workload, let's think of a different mapping. In this case, this is what we call an output stationary mapping. So notice how the loop nest changed. We basically swapped the P and R loops, and we made it go over R equals 0 to 3 at the buffer and 0 to 16 from the DRAM to the buffer. And once again, you can reason about the expected table. And as far as describing this mapping is concerned, it's a very simple changeover from the previous mapping. You can swap back and forth and see what the difference is. It's just these factors have basically changed. Okay, now let's move over to a more complicated problem. And what we're doing here is it's still a 1D convolution, but we're adding output channels to it, right? And so what that means is it's basically this K dimension. And so since we're adding output channels, your filter, you've got another dimension of filters, and you've got another dimension of output activations, but you did not change the number of input activations. It's exactly the same tensor. Excuse me. And so in the loop nest, you just have this additional K loop, and you can see that the K loop appears on weights and outputs, but not on inputs. So how do you represent this problem? Same thing. Think about the operation space and the various data spaces and the projections of the operation space onto the data space. So my dimensions now extend to K. So that's the operation space. For weights, my projection now has another dimension, which is K. And for outputs, again, I have the same K dimension. And inputs doesn't change from the 1D convolution because the K dimension doesn't affect inputs. Okay, and when I'm instantiating this, I need to, of course, instantiate the K dimension as well. All right, now let's talk about how you would map one of these problems into our known architecture from the previous example. And now we're going to examine two different mappings. One is what we're calling an untiled mapping, and the next is a tiled mapping. Okay, so the untiled mapping is not sophisticated. What we've done is we basically added the K loop to all of DRAM, right? So what this is going to achieve is it's moving over R, so that means it's output stationary. And so it's taken the output stationary loop and added the K loop on top of that. So just imagine you're running the previous kernel, but then you fetch a new block of, you basically rerun the same previous kernel, but on a block of new Ks at each sort of outer iteration. Okay, that's the untiled loop. And again, nominally, I added this K0 to 1 in our convention, using our convention. Okay, but we're also going to try tiling now. Okay, so we hadn't tried tiling before. So what tiling means is I take this K and I chop it up into multiple levels. So what I'm doing here is I'm basically storing a 3 times 2 or 3 times K2 tile at the buffer. And I'm going to be working on this tile. And then I'm going to be fetching a different block of Ks and Ps over time into the buffer. And the way you represent this tiled loop nest, it's just a straightforward evolution of the previous examples. The untiled mapping is very, very simple. You just need to add the K equals 32 dimension. The tiled mapping, again, it's actually fairly simple. You add this K equals 16 dimension here and K equals 2 dimension here, right? So in terms of representation, it's fairly straightforward. When you start actually doing the experiments, you'll hopefully start seeing some interesting numbers here. Now, I told you that this untiled loop is output stationary, right? What about this tiled loop? Is it also output stationary or is it something else? And to answer that question, what you should look at is the innermost loop. And the innermost loop is going over R, which is not changing outputs. So what that means is it's still output stationary. at least as far as the innermost loop is concerned. But then you move over to a new K, which is going to swap both inputs and both weights and outputs, right? So it becomes input stationary at this level, right? And so when you're thinking about stationarity, it's important to understand that stationarity actually is a hierarchical concept, okay? And to sort of dig a little bit deeper into that, here is, sorry, this is an eye chart. There's a lot going on. You may want to pause it and look at each of the rows and columns of this. I'm not going to walk through each and every example, but what this is trying to show is variants of data flows which are all output stationary, right? So we're working on the same problem shape. And this little table over here shows you the algorithmic minimum number of main memory accesses, which means this is optimal, right? You have to fetch this many from main memory because this is the size of your basic problem. And no matter what you do, you're going to be getting this many accesses. But then, depending on how you write out your loop nest, which is shown by some of these compacted, these are basically compacted loop nests, right? So depending on how you write out these loop nests, you can have a ton of variations in the number of actual main memory accesses that you get and the buffer occupancy or the tile size at each buffer, okay? And so again, please feel free to walk through all of these. All I'll point out is that they're still output stationary because the innermost loop, which is basically the innermost for all in these expressions, they're all over R. So they're all output stationary. Okay, so again, the point of the slide is, even though they're all output stationary at the innermost level, they're all different loop nests. And so when you think of stationarity, remember that it's a hierarchical concept. Okay, so moving on to an even more sophisticated architecture. You've done 2 levels now. 3 levels is basically a straightforward extension. There's nothing interesting. But what is interesting here is a new concept that we're introducing, which is called level bypassing. And what level bypassing tries to describe is, let's say that I, as an architect or as a programmer, decided that, you know what, I think the best use of my register file is to just store outputs here. I don't want to store weights and input activations here. And then because I'm storing output activations at my register file and I'm getting a great deal of filtering, I don't want to store outputs at my global buffer. I just want to store weights and input activations here. And then at main memory, I want to store everything, right? How do you describe this sort of a scenario? You do that using something that we call a bypass. And a bypass is part of the mapping, right? It's one of the ways in which you map a workload onto a given architecture. And in this case, what we're saying is, hey, Mr. Timeloop model, at the global buffer, I want to describe a bypass mapping directive. And within that bypass mapping directive, I want to tell you that you please keep the weights and inputs at this level, but bypass the outputs. And you notice in the comments here that it says same as default, which means if you don't specify keep, the model will assume that by default you want to keep it. And so you actually only need to describe the bypass, which is overriding the default. And so you're saying, hey, bypass the outputs here, and then at the register file, I want to bypass the weights and input activations here. Now, I said that this is the default. This is the default for Timeloop-model. Timeloop-mapper has no default. Because it's a mapper, it's going to look at all possible combinations, and it's going to tell you, hey, I think it's a good idea to keep outputs here, and I think it's a good idea to bypass inputs there, et cetera, et cetera. Okay, but we'll get to that. Okay, so why bypass? Well, bypassing avoids the energy cost of reading and writing buffers of certain tensors. And what you'll see is that realistically, you're not getting reuse for all tensors at all buffer levels, right? So sometimes buffer levels just end up being used as FIFOs, in which case it just makes sense to bypass those levels. So don't bother storing them. Now, if you bypass, there may be an additional cost in that your outer buffers, because you bypass, you may start seeing more accesses to those outer buffers. So it's a trade-off, right? You bypass the level, but now the capacity of that level opens up to other tensors. So you can store larger tiles for those other tensors, but at the cost of potentially filtering access for the tensor that you bypass. And so it's an interesting trade-off space. Again, the reason we have a mapper is to explore these sorts of trade-offs. But if you as a programmer know exactly what you want to do, then the YAML provides you a way to do that, right? But there's a nuance here, is that bypassing buffer levels does not change the energy cost of moving data over network wires. You bypass buffers, you can't bypass a network because you're going to have to pay the cost of bringing the data over wires or the network into the arithmetic units anyway, even though you describe to skip storage at a buffer level, okay? And so Timeloop takes care of that, and it pays the price appropriately. Okay, so I already spoke about the latter half of the slide, so let's skip that. Now we're getting into a really interesting architectural attribute, which is multiple PEs, or what we call spatial expansion of levels. And so what this is showing is it's basically the same architecture as before, but instead of one PE, I now have an array of PEs. I've got multiple PEs here, 16 PEs, for example. And the way to represent that in the YAML is really, really simple. What you can see here is the only thing that you need to change relative to the prior architecture description, which is you just need to instantiate an array of PEs. Timeloop infers everything else. Okay. In terms of mapping, though, something has changed, because now you need to describe how the computation is partitioned across those PEs, right? So previously, what were we describing? We were describing how tiles of data move between levels. Now we need to describe the partitioning of data across PEs. And we do that using what we call a spatial mapping level, or a spatial tiling level. And this describes the partitioning of data between the global buffer to the register file, because that's where the fan out was happening, right? And so we do that again using a loop nest, right? We say we declare a set of spatial fors, just like these fors, and we attach loops to them. And so it's just a loop base and bound, just like you did for the temporal loops, okay? And in this case, I chose, as a programmer, I chose to basically split the K dimension across the different PEs, across the 16 PEs, okay? And so in terms of representing this in YAML, it's actually not very different. It's just like, just like representing these temporal loops, but now I have a spatial block here. But within that spatial block, I'm describing factors and a permutation. Factors should be obvious. Basically, this is just, it's just telling you what this loop is doing. Permutation is a little bit more interesting, right? What does a permutation mean for a spatial block? What it's doing is, in this case, it makes no difference, because I only have K equals 16, everything else is 1. But if you had, let's say, 2 dimensions, if you had P and K, and you were unrolling both P and K across a space dimension of PEs, what that will change is the adjacency of what PEs are next to each other. So you can have P0, P1, P2, all corresponding to K0, then P0, P1, P2 corresponding to K1, and P0, P1, P2 corresponding to K2, right? Or you could flip that around. You could have K0, K1, K2 corresponding to P0, et cetera, et cetera. And what that changes is which PE is next to which PE. And again, what that affects is the cost of data movement, and whether a PE will be able to forward data to another PE or not. And so that's where the spatial permutation ends up being interesting. Okay, so that's how you write a spatial block in a mapping. I've already covered this, but I think what we're getting to is that specifying complete mappings manually is actually starting to get a little tedious. We've been describing these mappings, randomly, right? Maybe using some intuition, but largely randomly. And as these architectures become more and more complex, and remember, this is still a simple 1D convolution with output channels, right? So as your problem dimensions keep increasing, the complexity of your mapping keeps growing, right? And the sophistication of the thought process you need to come up with an optimal mapping keeps growing, right? It just becomes intractable at some point. And basically, it's a combinatorial explosion as we move to more complex problem shapes and hardware topologies. And that's what the mapper was built for. And so let's jump into the mapper at this point. OK, so to invoke the mapper, you still need to give it a problem, just like the model, and an architecture, just like the model. But instead of giving it a mapping, you give it these two things, a set of constraints and a set of parameters that are specific to the mapper. We'll talk about these as we move forward. Okay, but once you describe these to the mapper, it becomes the mapper's job now to construct what is a map space, extract mappings out of it, and then fire the model on mappings that it wants the model to evaluate, instead of we wanting the model to evaluate. Okay, so let's go back to a simple hardware architecture to understand how the mapper works, so which is the one from a prior example. There's no spatial levels here. It's still a 3-level architecture. Now, recall that for this architecture, we wrote a mapping that looks something like this, right? It had a set of factors and permutations, one for each level of data movement, okay? Now, what would the mapper do? Well, the mapper actually does something very, very similar. It constructs what we call a mapping template, right? So it kind of says, okay, oh, this is the architecture you want to map to? To map to this architecture, I need to create mappings that look something like this. I need to target the main memory, the global buffer, and the register file, right? But it says, oh, these are all blanks that I need to fill, right? So it needs to say, oh, I don't know what factors I'm going to assign. I don't know what permutations I'm going to assign, but this is sort of the overall template. And then what it does is it constructs what we call a map space. So map space is an enumeration of all of the ways to fill in these red blanks, right? And so what are all of the ways in which I can factorize my problem into these factors, which are basically your loop bounds? What are all of the ways in which I can permute my workload dimensions? What are all of the ways in which I can bypass bypass data spaces or keep them at all of the architecture levels? So bypass is not shown on this slide for brevity. But basically, a map space is an enumeration of all of the choices that the mapper has. Okay, and that space, it turns out, can actually be extremely large, right? I'm showing a 3-dimensional problem here and a 3-level architecture. Realistic architectures that we have can stretch to 5 levels, 6 levels, and a full convolutional layer is actually a 7-dimensional problem. That's basically a crazy combinatorial explosion. And in fact, most architectures don't have the flexibility to support every single mapping that you can construct using this formula. Okay, they're much more restricted. And so these map spaces need to be constrained by the user. Okay, and there's 2 classes of constraints. One is we call them architecture constraints, because what they describe is the architecture's own inability to go beyond these constraints. So here I've shown an example. Let's say your architecture was baked to be output stationary. Okay, in that case, the innermost level of this loop nest is going to go over R. That's baked into the hardware. I can't change it. The mapper is, if the mapper comes up with something else, it's an illegal mapping, right? So that's an architecture constraint. In addition to those architecture constraints, often users provide what we call map space constraints. So they are where the user is using their intuition to constrain the search space for the mapper. Because what happens is, despite these architecture constraints, some architectures are still so flexible that their map spaces are still huge. And so users often constrain the search space to make searching for the optimal mapping a more tractable problem. Okay, so you need to do that carefully, because you want to avoid skipping out on optimal mappings by providing a constraint that actually excludes the optimal mapping. So it needs experience and intuition, but you can do that. Okay, so given this constrained map space, the mapper runs a heuristic search over that map space, and we'll get a little bit deeper into that. Okay, now, as a user, there are several things that you need to tell the mapper, right? One is you need to tell the mapper what search heuristic to use. As of this recording, we have a set of linear heuristics that basically walk through the map space linearly. There's a random heuristic. They sort of sample mappings randomly within the map space. And there's a hybrid heuristic that kind of tries to do kind of a hybrid of linear and random search. There's a bunch of heuristics that we're always thinking about. There's active research going on in this field. And so this list is comprehensive only as of this recording, and it may change in future. So please stay tuned. There's another thing I should point out. If you look at the repo, you're going to see some random and random dash pruned. You should always use the dash pruned version of each heuristic and not the bare version. I'll explain what pruning does shortly. Okay, you also need to give the mapper an optimization criteria, right? What is it looking for as it's searching through mappings? How does it know whether mapping is better than the other? And that depends on the experiment you're trying to run as an architect. There's no universal prescription. So nominally, the model emits a set of statistics, of course. It emits a large number of statistics. What we've done is filtered a small set of them, and we've provided them as options for you to specify in the YAML as things that the mapper should look for, and it's a prioritized list. So in this example, cycles, energy states that, hey, Mr. Mapper, look for a mapping that gives you the minimum number of cycles. But if two mappings have the same number of cycles, then you should use the energy to differentiate between them. And this is a prioritized list of unlimited size. You can have as many stats in this as you want. And here's another example. If you want to do, if you want to just look at the last level accesses, for example, although I showed you a caveat right in the beginning why that's a bad idea, but it's just another statistic that the model provides, and so you can use it. Okay. Now, because these are all heuristic searches, the termination is the termination condition is also a heuristic, and so you as a user can tune the termination condition. If the map space is exhausted, that's not a heuristic, right? That means the mapper basically went through the map space. It was small enough, it actually finished searching through it and actually came up with the optimal mapping. So that's a default termination condition. You can also tell it, hey, look for a certain number of mappings, and that's it. Terminate after that. You can say, hey, look, if you find a certain number of invalid mappings consecutively, then just time out, forget it. I'll explain what invalid mappings are in a moment. Or if you say, you found a good mapping, and then for a very long time, you didn't find a good mapping after a better mapping after that, then you just declare victory and give up, right? Or if you just hit Control-C from the prompt, then you can terminate the mapper. But it actually ends gracefully even if you hit Control-C. It'll clean everything up and dump the statistics and dump the output. Okay, so let's do a little bit of a deep dive into how the mapper works. I already covered some of this. The mapper basically starts with a map space which is unconstrained, and then constrains it based on the user-provided architectural or map space constraints. But then even within this constrained map space, there are certain mappings that are illegal. And it's impossible for the mapper to know a priori which mappings are illegal before actually extracting them and telling the model, hey, model, what does the architecture look like? Will these mappings fit or not, right? So it's impossible to do a priori. So as the heuristic is going through the mappings, it is going to find some illegal mappings. There are also some superfluous mappings because there's certain factors that are one, and what ends up happening is that some permutations are basically trivial permutations because they're permutations of one, so they don't make any sense. And so in that case, those mappings can actually be pruned, and that creates this sort of pruned and constrained map space, which is actually not a very clean hyperrectangle, but it works, and Timeloop actually uses this. And remember, I said you should always use the pruned version of the heuristic. This is why, because it uses these pruned map spaces. Okay, so given a pruned and constrained map space, the mapper search heuristic basically samples a mapping from that, runs it through the model, and then completes the feedback loop and decides whether this mapping was better than some other mapping that it found before, and then decides what's the next mapping to sample. And as I said, there's a set of heuristics that we have. The mapper is actually also multi-threaded. So what ends up happening is that your pruned constrained map space actually gets split up into multiple sub-map spaces. And then the mapper actually forks off a bunch of mapper threads. And each thread actually runs an independent copy of the search heuristic. And each search heuristic runs an independent copy of the model. And so you've got this basically, very, very multi-threaded parallel search going on. And by default, the mapper application is going to query the host CPU for the number of available hardware threads it has, and it's going to fork that many mapper threads. Okay, so this is the last section of this tutorial. We're going to take a deeper dive into how the model does its job. So we're moving back into the model now. And so again, now we're at the model. So what we're trying to do is evaluate a specific mapping for a specific workload on a specific architecture. And if you remember what each mapping does is it basically determines the tiles, the set of tiles at various levels of the hierarchy, the spatial partitioning of the tiles, and the scheduling of the tiles over time. So what the model does is it constructs these things called point sets for each loop. What it's doing is it's constructing a point set for each iteration of the loop. So as you're moving through this p equals 0 to 8 loop, at iteration I and iteration I plus 1, what it's saying is, oh, at iteration I, this is the volume of data that I'm talking about, and at iteration I plus 1, this is the volume of data, other data that I'm talking about. And remember that this happens across both space and time. And then what it computes are these deltas, which is basically the set difference between the tile at iteration I plus 1 and iteration I. And these deltas are extremely informative. If it's a temporal loop, which means it's over time, the delta indicates stationary. So for example, if the delta is 0, that means the entire tile was stationary at that level. Okay. If the delta is non-zero, but there's sort of an overlap between adjacent tiles, then that means it's sort of a sliding window behavior, right? You've got a part of a tile that remains resident at this buffer over time. Across spatial units, these deltas indicate overlaps in data used between spatial units. So for example, you could have what we call a halo, which is some section of a tile that's used by two adjacent PEs, for example. And it also informs multicasting opportunities. So for example, if two adjacent units have exactly the same tile or exactly the same temporal delta over time, what that means is that to a parent unit that's talking to those and filling data into them, it can multicast that data, right? And it also informs forwarding, right? So if two units over time, they sort of share data, then you can reason that, this unit could have forwarded this data to this other peer unit. So all of this is information can be extracted from the delta. And so there's a step called tile analysis that the model does, which measures and records these deltas over all space and time. And a very naive but robust way to do this tile analysis is to actually simulate the execution of the entire loop. You basically run through the entire loop, all iterations of every loop, and say, oh, here's the tile, here's the tile, here's the tile. You construct this massive space-time view, and then you start reasoning about, okay, what can move data where? The problem is it's intractable. And remember, I said we're trying to get faster than real-time performance. And so fortunately, the problems that we're dealing with are so regular that we can make two assumptions. We can actually, for each loop, we can actually compute the first, second, and last iterations. Everything else is just regular extrapolations of those iterations. And the second thing we can do is that instead of actually performing computations on point sets or point clouds, we actually assume that our tile volumes are axis-aligned hyperrectangles, which is actually true for a large class of workloads, for example, convolutional layers. And if we do that, these delta computations become much, much more efficient. Okay, and so it's a combination of these two factors that allows us to be an order of magnitude faster than real time at evaluating the performance and energy of these workloads. Okay, so this is tile analysis. We're doing all this delta calculation, but how do we go from tile analysis to sort of microarchitectural stats? Well, that's where this microarchitectural model comes in. So the tile analysis sends to the microarchitectural model for each level of the architecture and for each network in the architecture, it sends sort of this fat data structure of, okay, this is the number of tiles you moved. This is the multicast and distribution pattern. These are the stats of the recipients. And then what the microarchitecture model does is it says, oh, okay, in order to have moved this much data from the main memory to the global buffer, I need to have made this many accesses to the DRAM. So the microarchitecture model is actually the module that understands microarchitectural attributes. Say, oh, this is DRAM. Oh, this is an SRAM of width this much. It's vectorized in this way, right? So it understands all of those microarchitectural attributes, and then beginning from this tile axis count, it produces a set of these microarchitectural statistics. It derives these, right? And there's a lot of interesting statistics it derives. There's address generators. How many times will address generators get fired? You know, are there spatial and temporal accumulations going on? We should be able to cover some of these details in the hands-on tutorial. Okay, and then starting from these microarchitectural statistics, we need to describe performance and energy efficiency. And so for performance, Timeloop uses this sort of throughput-based model. And the idea is that performance is basically the throughput of the rate limiting step across all of these levels in the architecture. So everything is assumed to be pipelined. And so the performance is basically limited by whichever is the slowest link in the pipeline. You know, these workloads run for long enough that initiation latencies are actually not that significant. Most of the time, your throughput dominated. And for buffers, what we use this, we either assume that they're double buffered, or we use this model called buffets, which actually allows for double buffering like advantages without actually incurring the cost of double buffering. And so what that means is you often don't have these sort of you know, microfill drain artifacts in the steady state as you move across the pipeline. Okay, so the buffet thing, I've included a reference for that in the on the slide. You can look it up if you're interested. Okay, so that's basically the performance. It's the throughput of the rate limiting step, and the energy is the summation of costs for various activities. I already showed you all of the various activities that are accumulated. So if you can sum up the costs of each of these activities, then you can get a total energy consumption. But then that raises the question of, okay, what are the per activity costs, right? How do you get the cost of accessing a register file of a particular shape? That's where Accelergy comes in. And that's basically where I'll end this section of the lecture. I'll just end with some future work that we're engaged in. I already mentioned search heuristics. We want to be able to expand the scope of workloads that Timeloop supports. And we also want to expand to be able to model compressed sparse architectures and the attributes of compressed sparse architectures. Once again, this is Timeloop. We aim to serve as a vehicle for good quality research on DNN accelerator architectures. The infrastructure is released under a BSD license, and you know, we'd like to invite collaboration in helping us make this tool better. Here's the set of resources that I showed on the first slide. Again, feel free to pause this video and look at it, look at the links. And I end my section of the presentation and turn it over to Nellie. Thank you all for your attention.
Okay, hello everyone. Welcome to the second part of the tutorial on Timeloop and Accelergy. I'm Nellie from MIT, and in this section, I'm going to talk in detail about the Accelergy tool in this evaluation system. So these are the resources that Angshuman has mentioned in the first section of the tutorial, where we have the tutorial website and some exercises related to this tutorial. So feel free to check out all these resources related to these tools. And if you have any questions, you can ask us during the live session of the tutorial or send us an email about it. So now let's dive into the Accelergy part of the tutorial. So as we all know that data and computation intensive applications have become very popular in recent years. And due to their nature, processing such applications on general purpose processors such as CPUs and GPUs are extremely energy consuming. So to solve this problem, hardware designers have been focusing on evaluating or designing various accelerator designs. So we could have the deep neural network accelerator designs, which were talked extensively by Ashu in the last section. And another example could be database accelerators that are targeted to the database processing applications. So since different types of these accelerators are optimized for different domain of applications, we have a very large and diverse design space of accelerators. So in order to quickly pick the most energy efficient design, we must be able to quickly evaluate the energy efficiency of arbitrary potential designs we have in mind in this large and diverse design space. So how do we do this? First, let's take a look at how a design is developed. At the very beginning, we will have an architectural blueprint of the design we have in mind, and we call this the architecture stage. Here we're showing a very simple general deep neural network accelerator architecture, which contains an on-chip global buffer and an array of processing elements, each of which is responsible for both locally storing data and perform multiply accumulation computations. So at this architecture stage, we tend to ask very high-level questions. For example, how many levels are there in our memory hierarchy, and how large are each of these levels? And specifically for the deep neural network accelerator, how many PEs do we want to have to meet the compute requirement, and how do we want to design them in terms of X and Y dimensions? By answering these questions, we're able to define a high-level architectural blueprint, which can be developed into an RTL model, which contains a complete hardware description of our design. The RTL model can then be placed and routed into a physical design, which can in the end fabricate it into a chip. So during this process of developing this potential design, we would like to evaluate energy efficiency of this initial architecture blueprint we started with. So traditionally, hardware designers have been focusing on evaluating energy efficiency at the physical layout level using physical level energy estimators. So these estimators take in the physical layout, perform simulations on the gate level components in the layout, and generate an energy estimation. So as we all know that since there are thousands of gate level components in the physical layout, performing such simulations usually takes a long time. Furthermore, if our potential design did not meet our requirement, we have to go back to the architecture stage and redefine our architectural blueprint. To do that, as you can see in the figure, we have a very long turnaround time for the evaluation of each potential design. Both the long simulation time and long turnaround time contribute to a very slow design space exploration with these physical level energy estimators. Furthermore, a lot of the emerging systems are using new technologies to improve the energy efficiency of the architecture. For example, a lot of DNA accelerators are using optical computation or non-volatile memory computation to increase the throughput of the architecture. Since building such emerging systems are even more complex than building the conventional digital design, such physical system development takes even more time, and using physical level energy estimators incur more overhead under such a situation. So being aware of this, we develop Accelergy as an architectural level energy estimator, which helps us to enable rapid design space exploration. So how does the architectural level energy estimation work? With an architectural level energy estimator, we perform the energy estimation right at the architecture stage. As you can see here, we're taking in the architectural blueprint at the architecture stage and perform energy estimations on the architectural level component in the design, such as a global buffer or MAC unit. Since there are much fewer such architectural level component than the gate level component, the simulation time of such estimations are much shorter. And furthermore, we can basically iterate through all the potential designs right at the architecture stage without generating any RTL model for them. And this results in much shorter turnaround time for each evaluation of a potential design. And both factors contribute to a faster design space exploration. So once we have arrived at the most energy efficient design, we'll then go ahead and implement the RTL model, physical layout, and finally fabricate it into a chip. So as we have mentioned, our Accelergy tool belongs to this category of architecture level energy estimator. So how does the architecture level energy estimation of Accelergy plays a role in the Timeloop and Accelergy system? So recall that for the Timeloop tool, we take in 3 important types of input: the constraints of the map space, the problem shape, and the architecture description. And Timeloop then performs the map space exploration on the architecture as well as the problem. So one of the most important metric that Timeloop wants to see for each potential mapping is the energy efficiency of the mapping running on the architecture. So in order to get the energy efficiency, Timeloop relies on the energy estimator to get the energy estimations. To do that, Timeloop sends the input architecture description internally to the Accelergy tool, which is able to use this architecture description to perform an energy estimation. Accelergy generates the energy reference table and sends it back to the Timeloop tool. The energy reference table records the energy per action values of each component in the design. By an action, we mean an operation that can be performed by a component. So in this example, we have the global buffer inside the architecture, and since it's a storage unit, it can be accessed, so it has an associated action called access. And in the energy reference table, Accelergy determines that every access to a global buffer takes 100 picojoules. With this knowledge, Timeloop is able to generate the energy efficiency of each mapping it evaluates. So at this point, you probably want to ask, why do we use Accelergy? Are there any existing tools that can perform accelerator energy estimations at the architecture level? So I'm going to briefly talk about some existing accelerator estimators and their limitations, and also go through how Accelergy solves these challenges. So the most popular type of accelerator estimator are called accelerator-specific estimators. So there are 2 example papers that implement such type of estimators. These estimators take in an architecture description, as we have mentioned, generally applicable to all the architecture level energy estimators. And the architecture description is composed of defined primitive components. By primitive components, we mean the basic building blocks of an architecture. As you can see here, each primitive component is defined with its associated hardware attributes. For example, the global buffer and local buffer are the storage components, and they are defined in terms of the width and depth. So the energy estimator will take in such an architecture description, and internally it stores an energy reference table, which is specific to the architecture it wants to evaluate. So in this case, it's aware that the architecture will compose of the global buffer, the local buffer, and the MAC, and it will store an internal table that corresponds to the specific architecture. Another input to such energy estimator is called action counts. Action counts describes the runtime behaviors of each component in the architecture, and this input usually comes from a performance model such as a cycle accurate simulator. So as we can see in this table, action counts describes the runtime behavior of each component in terms of the number of times its actions has occurred. So for the global buffer running a specific workload, we can see it's accessed by 10 times. Having both the architecture description and action counts, these types of energy estimators combine the information with the local energy reference table to do an energy calculation. Basically, this calculation combines the corresponding entries in the energy reference table and action counts to generate the energy estimate for each component in the design and to show that what's the energy consumption by running this specific workload. So this is basically the high-level flow of how these existing work generate the energy estimation. So what is the problem? Imagine that we do want to change the architecture. For example, we want to change the technology node from 45 nanometer to 65 nanometer. So now we have a completely new architecture. However, with these existing tools, the corresponding energy reference table do not provide the necessary information for this new architecture because it was internally stored and fixed specifically for the old architecture. Therefore, with not enough information, these external estimators will fail to perform the energy calculation of the new architecture with the new technology node. So with a simple example, we have already shown that these existing tools are not flexible enough with this fixed internal energy reference table to generalize the energy estimation to various designs in our design space. So Accelergy, being aware of this limitation of the existing tools, constructs a more flexible infrastructure that supports the modeling of the diverse architectures with various underlying technologies. So in order to do that, again, Accelergy takes in the architecture description with the primitive components defined by its associated hardware attributes. Instead of having a fixed internal energy reference table, Accelergy implemented the energy reference table and area reference table generator, which is flexible enough to generate an energy reference table for each architecture it sees during runtime. And furthermore, Accelergy understands an architecture description in an object-oriented fashion. So more specifically, in each architecture, each component belongs to a primitive component class. So here, for example, both the local storage and global storage are instances of the SRAM primitive component class that can be understood by Accelergy. And this object-oriented approach reduces the complexity for Accelergy to perform the energy reference table generation. So how does the energy reference table generation work? First, Accelergy will identify the component in design. In this example, the global buffer is identified by Accelergy, and Accelergy is able to capture both the hardware attributes of the global buffer as well as the premium component class that it belongs to. The energy reference table generator queries a primitive component library that's stored in Accelergy, which summarizes the common primitive component classes that are popular in accelerator designs. Of course, user can supplement this library if they have their own primitive component. So inside the primitive component library, Accelergy will realize that for SRAM class components, they have an action associated with them called access. Therefore, Accelergy will send a request to external energy estimation plugins asking for the energy consumption of this access action associated with the specific component it looks at. So an example simple estimation plugin will contain information that are related to a component in the architecture. So here we're showing a very simple example where the plugin contains a database which stores the energy consumptions of the various components in the architecture. So by receiving the request, this estimation plugin will find the most matching entry and sends back the energy and area results all the way back to the energy reference table generator. So usually we will have multiple of these estimation plugins, and Accelergy will pick the most accurate energy estimation plugin to perform this estimation. With the result returned back to the energy reference table generator, Accelergy will populate an entry that's related to this component in the energy reference table. And the same actions will be performed for all of the components in the architecture, and then a energy reference table specific to this architecture input is generated during runtime. So as you can see that Accelergy is also able to generate area reference table, which depicts the area of each component in the architecture it parses. And the second step for this energy estimation process is to calculate the energy consumption of each component when they are running a specific workload. So Accelergy has an energy calculator which is able to combine the energy reference table information with the runtime action counts of the component. Recall that this runtime action counts usually come from a performance model, and it records the runtime behaviors of the component in design. So Accelergy combines the energy reference table it just generated with the action counts to generate the energy estimations of each component in the design. So as you can see here, if we run a different workload on the same architecture, we do not need to regenerate the energy reference table as the components in the architecture didn't change. We only need to rerun the simulation to have a different action counts. So this two-step process also reduces some overhead related to the ERT and ART generation. So now let's take a look what would happen if we change a component in the architecture. So now we have changed local buffers technology node. So what the system will do is Accelergy will realize now we have a new component which is of 65 nanometer, and it will ask the plugin whether it supports the 65 nanometer component, SRAM component with a specific hardware attributes. So in this case, our plugin is able to support this kind of estimation, and the ERT will be updated, and therefore the final energy estimates will be generated correctly. So in this case, when we have a new architecture, we can just plug in a new plugin or have additional information in our existing plugin to support this whole process of energy generation. And all this flexibility will allow Accelergy to actually generate energy estimations of various architectures with various underlying technologies. So we have been using a simple estimation plugin example, but actually our estimation plugin can do a lot more than just providing a plain number. So we have shown that using a very fine-grained classification of component runtime behaviors inside the estimation plugin, we can improve the energy estimation accuracy of specific designs. So what does that mean? So for example, now we have a fine-grained action classification of a component inside our plugin. And we are using a component which is a multiplier with a zero gating optimization. The zero gating optimization refers to the fact that the multiplier will gate its computation when it sees a zero in its operand. So on the left, we're showing some energy characterizations of this zero gated multipliers. We're showing 3 different types of fine-grained actions. So instead of only saying this multiplier can do a multiplication, we further classify this multiplication action into 3 different fine-grained actions. They are the random multiply, the reuse multiply, and gated multiply actions. The random multiply refers to a normal multiply where its 2 operands are constantly changing across consecutive cycles. Therefore, basically all of its wires are switching during this computation, resulting in very high energy consumption. And the second action, reuse multiply, refers to the fact that one of the operands stay constant across the consecutive cycles, making the wires related to this operand idle for this computation. Therefore, there is a reduced energy consumption related to this optimization. And the third type is the gated multiply, which refers to the fact that one of the operand to this multiplier is actually 0, and therefore the entire multiplier is 0 gated, resulting in idle wires basically everywhere in the multiplier. And this basically results in a very low energy consumption of the multiplication. So with this final classification of the action types, we can basically have multiple entries for this multiplier with various actions in our energy estimation plugin database. And how does this help us to improve the energy estimation accuracy? As you can see in this graph, the x-axis are showing various PEs in an architecture, and each PE is processing data of different sparsity. And inside each PE, we have this zero gating optimization applied to the multiplier. And on the y-axis, we're showing the total energy consumption of each PE. Since each PE is processing data of different sparsity, the zero gating optimization brings different amount of savings in terms of the multiplier energy consumption. So with the awareness of the various action types, Accelergy is able to capture these differences across the PEs, which have different workloads. And another question you probably want to ask is, okay, so we are only looking at high-level action types. How does it compare to the actual estimation using the gate-level components, which captures more runtime behaviors of the lower-level activities. So now we compare the Accelergy estimation to a ground truth, which is generated using post-layout simulations of the architecture. So the post-layout simulation basically simulates the behavior of the gates in the design, and actually it also simulates the real data that's sent into all of these gates in the design. So comparing to the ground truth, we can see that not only is Accelergy able to capture the chance across PEs brought by this optimization, it is also able to have a relatively accurate absolute energy consumption estimation for all of these PEs in the design. So with this characterization provided in this plugin, we're able to use a higher level classification of fine-grained actions to actually produce a very accurate estimation of the components in the design. Another example is a fine-grained classification of the memory access types. So in here on the left, we're showing the various access types related to a register file. And the random read refers to the fact that we're reading different data from a different address in consecutive cycles. And this results in toggling of all of the wires in this register. And the repeated read refers to the fact that we are reading the same data out of the same address across cycles. So these are the two types of read actions. And we also have classified 3 types of write actions. Random write is similar to random read, where all of the addresses and data are different across cycles. Repeated write, meaning we're writing the same data to the same address. And constant data write means the data is always the same, but we're writing it to different addresses, which results a little more toggling in terms of address wires, but idle data wires. So as you can see from this figure on the left, across all these different action types, we actually at maximum have 5x difference between a random write action and repeated read action. So instead of only classifying the action of a memory component as an access, we can actually have a better characterization of all these actions using a fine-grained action classification. And on the right, we're showing how is Accelergy doing for capturing the energy consumption of various local memories inside the PE as well as the Mac. So there are 3 different scratch pads on the x-axis, which are all local memories inside the PE, and the y-axis is showing the total energy consumption of the components. So as you can see here, Accelergy is able to use these fine-grained action types to capture the energy differences between the between these scratch pads, and also it produces a relative accurate energy estimation in terms of total energy consumption. So we have been talking about energy estimation plugins. So what types of plugins can we plug into the Accelergy tool? So of course, we can have traditional open source plugin, for example, Cacti and the 45 nanometer open source library, where Cacti is responsible for performing memory storage estimation and cache estimation, and the 45 nanometer, of course, is data related to the 45 nanometer technology node. We can also, as Asha had mentioned, plug in our proprietary plugins if we have access to our own data with, so basically we'll construct a plugin locally and plug it to Accelergy without making it open source. And also we can have plugins that targets emerging technologies, for example, non-volatile memories. This can support us to estimate various energy consumptions of these emerging systems. So we have provided in our Accelergy framework 2 open source estimation plugin. One is the Cacti estimation plugin that performs the SRAM and cache energy estimation, and the other is the 45 nanometer estimation plugin, which supports various type of arithmetic units as well as some memory components. So this basically shows a high-level structure of Accelergy's modeling of a simple architecture. But actually, in reality, a lot of the designs are more complicated than just a global buffer and a PE. So due to their complication, they actually involve many more primitive components. So here we're showing an example which is called a smart buffer, which is a storage unit with pre-programmed address generators. So on the right, we're showing basically an architecture organization of the smart buffer unit, where we have AG is the address generator. We have two address generators for generating the read addresses and write addresses. And we have the buffer, which is the SRAM unit that is responsible for storing data in the storage unit. So the address generators are pre-programmed to generate sequences of addresses, and these requests will be sent to the storage unit buffer, which will either write data into a buffer or read data out. So as we can see here, the address generators basically are modeled as adders, and they belong to the adder class, and the buffer belongs to the SRAM class. So what's the motivation of having this kind of storage unit? So basically for domain-specific applications, they have very predictable storage access patterns. So for example, if we are doing general matrix multiply applications, we know we want to access row by row for each matrix operand. Therefore, with this knowledge of these domain-specific applications, it is useful for us to actually pre-program all the access sequences inside the smart buffer instead of have a centralized control unit that incurs a lot of overhead for either performing calculation of addresses or sending the calculated addresses to these local buffers. So now let's, instead of having this simple architecture design, we can enrich it with this new practical storage unit. So we can add all the address generators to the global buffer storage and the local buffer storage. And furthermore, we're adding a FIFO unit to the Mac component because we do want to store some of the output of the Mac to enable higher throughput. So this is a slightly more practical architecture design, but as we have seen in the last section, we actually have the spatial property of the architectures, where we probably will have many more PEs to perform parallel computations, which allow higher throughput in our accelerator. And in this case here, we're having a very common architecture design for a deep neural network accelerator. So now let's send this architecture description into Accelergy. As you probably have realized, we have a much more tedious architecture description. And if you want to make modification to this architecture description, you have to navigate through all these primitive components involved in the design, and it can be hard to make modification and is very error prone. And furthermore, if we look at the action counts that will be sent into the Accelergy framework, we will see that we need to capture the runtime behavior of each of these pre-new components involved in the design. So instead of only capturing the buffer and the MAC operations inside the PE, we now have to pay attention to the address generators as well as the FIFO unit. So with this action counts, we can see that we have even more tedious generation of the action counts. And since we need to capture more components, the simulation time will significantly slow down in our performance model. And also, if we make a small modification to the architecture, we basically have to regenerate this action counts because some of the components' runtime behavior has changed. And this makes the evaluation turnaround time to be longer because we have to rerun the simulation every time we make a small update. So we should solve this problem. And are there any existing tools that try to model such complicated architectures? So as we all know that CPUs and GPUs are very complicated architectures, and there are actually existing tools for architectural level energy modeling of them. So what they do is in order to reduce the complexity of our architecture model as well as the runtime action counts, they use a fixed set of compound components to represent the architecture. By compound component, we mean high-level components that can be decomposed into lower-level components, such as primitive components. And in this case, since general-purpose processors architectures are fairly regular, one architecture model can basically represent a wide range of such architecture designs. However, if we try to match our accelerator design to the existing models, it becomes really hard because our accelerator are specifically optimized for a specific application, and the optimization applied to each accelerator will be different. So it will be not sufficient for us to provide a fixed set of compound components that that is able to model the various accelerator designs in a diverse design space. So being aware of that, accelerator infrastructure implements a mechanism that actually supports the succinct modeling of the complicated architecture in the very diverse accelerator architecture space. So first, similar to existing work, we use compound components in our architecture description. But since a lot of accelerators have their own optimization to their hardware, we actually allow architecture descriptions with user-defined compound component classes. So you probably have noticed here we have very simple architecture description. However, the global buffer and the local buffer are of smart buffer class, which is user-defined and is composed of the address generators and the actual storage. And we define the MAC to be a MAC FIFO class, which is again user-defined and is a high-level class that has lower-level subcomponents. So in order for Accelergy to understand what each these user-defined classes are, we also allow user-defined component hardware architecture using premium components. So here we're showing that we're providing compound component description for all of these user-defined compound component classes. For the smart buffer class, we have the two address generators, each of other primitive component class type, and the actual buffer, which is an ASRAM. And similarly for the MAC FIFO compound component class, we have the FIFO and MAC as primitive subcomponent of this compound component classes. So with this, Accelergy is able to understand what each high-level compound component is in terms of the primitive components. And furthermore, we also allow user-defined compound actions using primitive component actions. So this information also belongs to the compound component description. Now let's think about this smart buffer class and its associated action rate. So according to the definition of the smart buffer class, a read of the smart buffer involves a generation of the read address using the address generator, which basically resolves into an add operation of the adder, and also a read into the actual storage inside the smart buffer, which basically results into a read access into the buffer storage. So with this definition of a high-level compound action, Accelergy is able to understand how this high-level action can be decomposed into lower-level actions associated with a primitive component class it knows the definition of. So now let's relook at how we can represent this architecture design. Accelergy then takes in architecture description in terms of high-level components. Each of them is an instance of a user-defined compound component class, and each class is defined inside the compound component description. So in this way, if we change the definition of the compound component, we only need to modify the compound component description. The architecture description can stay the same. And the architecture description is definitely more succinct than the previous version we had several slides ago. And now let's look at the action counts. So since we have defined the high-level actions associated with each compound component, the action counts becomes much simpler too. The actions here in the action column now refers to the high-level actions of the component. So when we say a read of a global buffer, it actually refers to the compound action read, which it can be decomposed into an address generation and access to the storage. So you probably then have noticed if we change some definition of the compound component, which thereby change the definition of the compound action, but this does not require us to rerun the simulation of our architecture because the high-level behaviors of these components stay the same. So in this way, both the architecture description becomes much more succinct, as well as we're reducing the amount of overhead related to generating the energy estimation of a new design. So now here we summarize the actual high-level infrastructure of Accelergy. Accelergy takes in two input to describe the design, which is the architecture description composed of high-level compound components and the definition of these user-defined compound components, which are encoded in the compound component description. So these two files will be parsed by Accelergy, and the energy reference table and area reference table will therefore be generated. The action counts describes the runtime behavior of each high-level compound component in the architecture description. So Accelergy will then combine the energy reference table with the action counts to generate the energy estimations of this design. So this basically summarizes the high-level infrastructure, and more details about how we represent the architecture, how do we define the compound component classes, and what does the ERT, ART looks like will be explained more during our hands-on session using the exercises. So now let's see how Accelergy is useful. Does it perform accurate estimation on the various accelerator designs? So we first perform a validation on a conventional digital DNA accelerator design, which is ARIS, and we run AlexNet with ImageNet input feature map on it and compare it to the ground truth generated from the post-layout simulations. So a very brief introduction to the ARIS architecture. So ARIS architecture has two types of global buffers. One is the shared global buffer that can store both the input feature maps and output feature maps, and it also has the weights global buffer for storing the weights data. And it has an array of 168 PEs, which is 12 by 14, and there are 4 different networks responsible for sending data back and forth between the global buffer and the PE array. And inside each PE, we have 3 different types of local buffer. Each of them is responsible for storing a specific data type. And we have the MAC unit responsible for performing multiple accumulation operations. And one important optimization applied to this architecture is the zero gating optimization, which refers to the fact that when there is a 0 input feature map data, we do not want to read the weights data, because no matter what the rate is, the MAC output will be, the multiplier output will be 0. And also we want to gate on computing of the MAC because one of the operand is 0. So this results in 2 fine-grained action types, which are the gated read action on the memory storage component and gated MAC action on the MAC component. So as we have mentioned, we have achieved 95% accuracy for in terms of total energy estimation comparing to post-layout energy. And here we're showing the relative energy breakdown of the various components or important units in the design. As you can see that the P array is the most energy consuming part, as we are performing most of our computations inside the P array. To elaborate both the local data reuse and the MAC optimization. And we also have the networks and global buffers. So as shown in these figures, Accelergy is able to capture relatively accurately in terms of the energy breakdown across these components. So let's first, since P array is the most important part of this design, let's further take a look into the P array energy breakdown. So this figure shows the Accelergy estimation ground truth and also comparison to existing work called Aladdin, which is a very popular energy estimator for accelerator or modeling tool for accelerator designs. So this figure shows the energy breakdown of the PEs across the array. The x-axis again is the various PEs in the P array, and each of them is processing data of different sparsity. The y-axis is the total energy consumption of this P array in terms of microjoules. So as you can see that Accelergy is again able to capture the chance as well as the absolute energy consumption of these PEs. Aladdin, on the other hand, does not classify fine-grained action types, and therefore it will always say that the MAC computes a MAC operation instead of being aware of the fact that the MAC can actually be gated when it sees the zero gate data. Therefore, the various sparsity processed by each PE does not make a difference for Aladdin in terms of the energy estimation. Therefore, you can see a very flat line across the various PEs, even though the zero optimization actually brings different amount of benefits to these PEs. And then we also want to see whether Accelergy is useful when we have a design with emerging technologies. So we perform a modeling of processing memory-based deep neural network accelerator design using Accelergy. So as a very brief background of processing memory architectures, these architectures uses memory cells, a memory cell array instead of digital MAC array to perform the multiply accumulation operation. So since all these calculations using memory cells are in the analog domain, we actually have the DACs and ADCs to convert between the digital storage and the analog computation. So in terms of the analog computation, at a high level, the input activation is sent into the word lines as voltages, and the weights are programmed into the memory cells. So these are actually weight stationary architectures. With the weights programmed into the memory cells, we can use Kirchhoff's current law to actually perform the MAC operations across the bit line of the memory array, and what comes out of each bit line is actually a partial sum. So with this setup of the architecture, you can see that it's very different from a conventional architecture. Not only that it's using a different underlying technology, but also the actual organization of the architecture is different. So how do we use Accelergy to model such architectures? Again, Accelergy takes in the architecture description, which is the global buffer and a bunch of we still say each computation unit is a PE. And if you notice that the class of these high-level components are PIM related. So for the global buffer is actually an instance of the GLB PIM compound component class, which is user-defined. And what's inside this high-level compound component is actually the SRAM storage, similar to the conventional design where it stores the digital data, but it also involves the A to D and D to C, A to D and D to A component for performing the convergence between the digital and analog domains. And similarly, for each MAC unit in the PIM domain, this definition also is related to the a memory cell. So here, each memory cell stores 1 bit. So in order to perform a 16-bit MAC unit, in this component, you will have multiple of these memory cells. So Accelergy would need an external energy estimation plugin that supports estimation of such new components involved in the design. So here we're showing a very simple example where this plugin is specifically for performing energy estimations of memory cells as well as ADC and DAC component. And with this, we take in the action counts of the components in the design and generate the energy estimation for this design. So this is at a high level how Accelergy can be adopted to modeling such emerging technology-based architectures. We also provide the infrastructure with Accelergy and Timeloop with parameterized architecture template as well as component design templates to allow easier modeling of such PIM architecture designs, where the architecture template allows us to change the architecture level parameters such as number of PE rows and columns or the size of the global buffers. And the component design templates allows the users to redefine the compound component contents of the high-level component in this architecture. So for example, if we have applied some optimizations to the ADC component, we can redefine this high-level component inside the component design template. And of course, we have open sourced a very simple set of processing and memory-based component estimators as a plugin to support our example design. So then we try to validate our energy modeling of this processing memory-based design. So we validated on the ADC-based design proposing Cascade. And in terms of design specs, we have 80 64 by 64 1-bit memory stir arrays. We have 1-bit DACs, 6-bit ADCs, and we use 16-bit data representation for input activation weights and partial sums. And we run VGGNet convolutional layers on this architecture. For external energy estimation plugins, we basically constructed a database with numbers extracted from the paper or its cited source. Here we're showing a validation in terms of the total energy consumption across the VGG layers, and this energy is breakdown into the various components in the design. As you can see that we have a very close energy estimation in terms of total energy consumption, which is 95% accurate. And we also are able to track relatively accurately in terms of the breakdown across the various units in the design. And here, unlike the conventional architecture, we also need to consider what's the most important most energy consuming part in this architecture. And from this figure, we can see that Accelergy tells us the analog to digital convergence system is the most energy consuming unit of this design. And here we're showing the energy breakdown across the various VGG convolutional layers captured by our Timeloop and Accelergy system. And you can see that we not only are able to capture the total energy consumption, we're also able to capture the per layer energy consumption, and as well as the actual energy breakdown across the various components inside each layer. So this basically concludes the Accelergy part. And as a summary, Accelergy is an architectural level energy estimator, and it allows us to explore the design space in a much faster way. It provides flexibility to describe and evaluate a wide range of accelerator designs, and it also supports different technologies with user-defined plugins. We are able to show that we can achieve high accuracy energy estimations for both conventional digital design arrays and a processing memory-based accelerator. So the Timeloop Accelergy system allows us to perform fast explorations on both the high-level architectural properties and as well as the lower-level implementation optimizations on the various components, such as when we have a storage unit with local address generators. And here is a reminder slides of all the resources that are related to this tutorial as well as the tools. So feel free to check out all these links for the exercises and examples related to our system. All right, so this concludes the Accelergy part of the tutorial.